Okay, students. So, we previously discussed entropy, and we discussed spontaneity and Gibbs Free Energy, and now we'll finish up by relating Gibbs Free Energy to equilibrium and the idea of standard and non-standard state conditions. So let's go ahead and get started. So the idea here is, the slide is, what does it mean when you're not at standard conditions? What does it mean when you're not on standard state conditions? Well, the one obvious possibility is that the temperature is not at 298. It's a little bit hotter, a little bit colder, and that will affect the spontaneity of a system. But another possible thing is that what happens when not all compounds are at 1 molar and 1 atmosphere? So remembering back our equilibrium quotient Q, that Q was a snapshot of our reaction saying that products over reactants at the given time. Under standard state conditions, all solids and liquids would cancel out, and everything that's at 1 molar or 1 atmosphere would be 1 divided by 1 divided by 1, or times 1, so it would be 1. You would have a Q of 1 at standard state conditions. Well, when K, our equilibrium constant K, is not 1. It almost never is 1. So when we're at standard state conditions, Q is not equal to K. We're not at equilibrium, and so reaction will proceed until it achieves equilibrium. Remember that Q must always shift until it equals K. Well, we have a direct way to relate Gibbs standard with Gibbs non-standard. That Gibbs standard plus R times T, so gas constant R, 8.314 joules per mole Kelvin, times T, times the natural log of our equilibrium quotient Q. If you do that, you can the Q of our scenario, we can figure out how much more spontaneous or less spontaneous is this than our standard state conditions. Bringing it back to Le Chatelier's again. Le Chatelier says if you add more reactants, you're going to go towards products. Well, if you add more reactants, your ln of Q becomes negative. So when you add more reactants, your ln of Q becomes negative. You add a negative RT-ln-Q to the Gibbs free energy. What happens to the Gibbs non-standard? It becomes more negative. It becomes more spontaneous when you add reactants. When you add products, ln-Q becomes positive because the natural log of a number greater than 1 is positive, and so your Gibbs non-standard becomes smaller. So when you add products, a reaction becomes less spontaneous based on this natural log of Q. Well, when all of the concentrations are 1, when we're Q equals 1, the natural log of 1 is 0. So the definition of Gibbs and Gibbs standard is that when equilibrium constant Q is 1, we are at Gibbs standard state condition. That these two values, Gibbs non-standard and Gibbs standard, are the same. Now, as I said, Gibbs non-standard approaches zero as a reaction approaches equilibrium. But delta G standard cannot change. It does not change because it is an artificially defined point in a system. The point where all concentrations are 1. So what we can do is that when Gibbs non-standard is 0, we are at equilibrium. So we can look at the delta G standard plus RT ln K, so that Q has become K. This sum must equal 0. So rearranging this, we have a new way to calculate K if we know our Gibbs free energy. Or if we know our K, we have an easy way to calculate our Gibbs free energy. So we can directly relate Gibbs free energy to our equilibrium constant K. Notice a large K, which is a product favored reactant, would have a positive ln K, which, because this is a negative RT ln K, would make this a spontaneous system. When K would be small, ln K would be negative, and negative becomes a positive. We have a non-spontaneous system. So we can directly understand how a system is going to move based on the size of K or the Gibbs free energy and relate the two. But what is probably more profound is now we have an easy, practical way to calculate a K value at any given temperature. K was very easy to calculate at 298, given we had some concentrations, but K at other temperatures was very difficult to find. You would have to set up that whole reaction and run the values again. Well, here, since we're looking at Gibbs standard, we can calculate Gibbs standard from enthalpy and entropy. And you can find Gibbs standard at another temperature using enthalpy and entropy and minus the enthalpy minus T delta S. Delta H minus T delta S can find you the Gibbs free energy at any temperature. From that in mind, we can use that to find our RT ln K. So we can directly see how these two relate. And so you can rearrange the equation to look at K is the inverse natural log, that's that E exponential, of the negative delta G over RT. Making sure to convert Gibbs into joules. Units must cancel for this to work. Delta G needs to be in joules because R is in joules. But if you can do that, you can easily find K at any temperature. Now, we have two last problems. Looking at our 3H2 again, and N2 goes to 2NH3. 3, 1, and 2. We have a Gibbs of 33.9. I'm wondering, since we're out of standard state, is this guy going to be more spontaneous or less spontaneous? Is this guy going to be more spontaneous or less spontaneous? So let's look at it. Our Q. So our equation is going to be delta G equals delta G standard plus RT ln Q. Our Q is going to be products squared over reactants, or products raised to the power of their coefficients. Products over reactants raised to the power of their coefficients. So 4 over 27. 4 over 27. That's what we have. So Now the natural log of 4 over 27 is RT times negative 1.90, let's say 95. It's at 298, so we're going to times 298. 8.314. 9095. 298 times 8.314. You'd get a really big number. Really, really big number. But we got to divide by 1,000. Why do we have to divide by 1,000? Because R is in units of joules per mole Kelvin. And so the effect is only 4.73. So when we add our delta G standard, so we have negative 33.9. Yeah, 33.9. And we negative 4.73. It becomes more spontaneous, but not by a ton. So delta G non-standard at this situation is negative 38.6. It's more spontaneous, but not by a ton. It's not going to suddenly explode with products, but it is more spontaneous. And you can figure that out. How you can figure out how to make this more spontaneous by manipulating this reaction. So this RTLNQ is going to provide minor tweaks. It's usually not going to be a huge change, but it is a change. So it is a real change that you need to consider. What is the Gibbs for this reaction? O plus ozone goes to 2O2. So what's the Gibbs and what's the RTL and Q? O2 is going to be 0, 230.1, and 163.4. Okay. So DocCam. Okay. Here we go. So products minus reactants. So 163.4 and 230.1. Delta G is negative 393.5 kilojoules. This is a very spontaneous reaction. However, due to concentrations and other factors, this is not super spontaneous. I mean, it doesn't happen kinetically very fast at all due to sheer concentrations. It's very, very dilute situation, and so this does not actually happen very fast, even though this is wicked spontaneous. So delta G standard equals negative RT ln K. Let's start by, so we say negative 393,500 joules. I'm going to divide that by negative 8.314 and 298. So 3935 times 1,000 divided by 8.314 divided by 298. Still a big number. So we have 158.8 equals ln K. This is actually as far as we can go on most standard calculators, because if we try to do an inverse log of this, okay, well, we can actually go a little bit farther, but some problems, if you try to do an inverse log of them, it will overflow your calculator. Now, in this case, K equilibrium would be 9. We'll say 0.48 times 10 to the 68th. It is incredibly product favored. It is incredibly product favored. So much so that, yeah, you would see essentially no reactants left. So, with that in mind, this is where I leave you. That sometimes you won't be able to calculate it any further, but try it, see what happens. But if you can't calculate it further, leave it as LNK. But that's okay to have an incredibly huge number, because that just means it wants to happen. We have an incredibly spontaneous system. We have an incredibly product-favored reaction. But that is where we leave this chapter. We have learned the idea of entropy. We were able to calculate entropy of the universe. We learned about Gibbs Free Energy. We learned how Gibbs Free Energy depends on temperature. And then we learned the idea of standard versus non-standard and how to directly relate Gibbs Free Energy to equilibrium constant K. For the next chapter, we will look at electrical reactions, redox reactions. We will look at reactions that produce electricity, and we will eventually relate them back into Gibbs, and we will relate them back into K when it's all said and done. But in the meantime, this is where I leave you. Have a good day.